let's talk about the speed of waves, the velocity of waves real quick here. Let's say over here you have an inquisitive little bird. And Mr. Bird here is sitting on a little pier out in the ocean. So the ocean is out here, and he's watching the waves come in. Like this. Now let's say if there were no waves, then that is where the water level would be on this pier. But there are waves today, and so that's what it looks like. First of all, this is what we'd call a transverse wave. The wave itself, the disturbance, is moving this way, let's say, towards Mr. Bird. But the individual particles would be shaking up and down, up and down. So we would say the direction that the medium moves is perpendicular to the way that the wave moves. And so a water wave would be an example of a transverse wave. So let's say Mr. Bird here is thinking about the velocity of this wave and how he can calculate it. Well, as any good bird knows, he knows the equation for velocity is simply distance over time. And you can still use that equation now. It's perfectly valid. If you knew how fast the wave was, or how far the wave went, and you knew the time it took to travel that, you could use velocity as distance over time. In fact, some of the problems that you're getting ready to do use this simply the distance the wave traveled divided by the time it took to travel that distance. Now, one thing to watch out for whatever reason, physics textbook writers love to pull this little trick, and there's a few like this on the problems you're getting ready to do. They'll say like a wave goes to the bottom of an ocean and back, or an echo goes to like a wall and back. So then you have to realize that the distance that they're talking about is actually only half of that. So if they say a sound wave goes to the bottom of the ocean and back, and then they ask how deep it is, they're just talking about half that distance, or you could take half the time. Whatever, it doesn't matter. So let's look at a few things on this wave and label them just so we make sure we can remember what they're called. So one thing is the distance from the crest to where the rest position would be if there was no wave at all. That is called the amplitude, and I'll label that right there. And theoretically, these would all be the same. The distance from that rest position to the bottom of the trough would also be the same. That would also be the amplitude. So either one of those can be called the amplitude there. And then this distance from the crest of this wave to the crest of that wave. So from one cycle to another. You could just as easily done the trough to this trough. This is called the wave length. And so an important equation here, or important symbol here, is this one right here. And this upside down looking Y thing is actually the Greek letter lambda, and think of it, it's an L, think of it as L for length. So we can just use that symbol to represent the wavelength right here. So let's take this equation and modify it a bit for waves. Let's say Mr. Bird is going to look at the distance in time, but a convenient distance would be from this crest to this crest. So let's say he starts counting when this crest reaches him, and it moves along, and he stops counting when this crest meets him. Then for this distance here, we know that it is the wavelength. That's the distance that it traveled. So let's just pretend that this was 3 meters here from crest to crest. Then if he starts timing here and stops here, then the distance the wave traveled is equal to 1 wavelength. That time, we already have a word for that, for one complete cycle to happen from crest to crest. That time is called the period. So I'll write, instead of a lowercase t, a capital T for period. So this is the exact same equation for velocity. It's still distance over time. It's just we've picked our distance to be equal to a wavelength, and we've picked our time, therefore, to be equal to one full period. Now this equation and this equation, they're the same thing. There's one more way we often write it. If you remember from the other day, we said period is equal to 1 over the frequency, or you can say frequency is equal to 1 over the period. They're inverses of each other. So what we can look here is, look, here we have 1 over the frequency, 1 over the period. Dividing by the period is the same thing as having the frequency there. So the more common way of writing the wave speed equation is that the velocity of the wave is the wavelength times the frequency there. This would be in meters. This would be in hertz, which is really a way of saying per second. So this would be in meters per second, which is a velocity. So that is how you get the wave speed equation. Now, one important thing is this velocity in any given medium is fixed. So v is fixed in a given medium. So for example, sound waves right now in the air, they're going a fixed speed, about 340 meters per second. And that's true no matter how big the amplitude is. So if I make a louder sound, it's still going 340 meters per second. If I make a softer sound, it's still going 340 meters per second. That doesn't change it. And you could make a low frequency sound going 340 meters per second, or a high frequency sound going 340 meters per second. So the velocity never changes. So one thing we need to look at is, and in class I would demonstrate this to you on a Slinky or something, if this velocity can't change, and let's say you raise your frequency, you make your voice higher pitch. If velocity can't change, but frequency goes up, and let me symbolize it like this. We have a velocity, and we have a really big frequency, a high-pitched sound. Then what has to happen correspondingly is we get a small wavelength. So big frequencies go with small wavelength. But because that velocity can never change, what if we made a really low frequency, a really small frequency? Then, because this velocity always has to be the same number, we'd have to have a really big wavelength. So low frequencies go with big wavelengths, high frequencies, big frequencies go with small wavelengths.